Okay, so again, if we have some initial function y equals f of x and it has these four ordered pairs on it. I completely made these up. There's no rule for this. These are just random numbers I just picked out of thin air. But what we'll do is if we have the inverse function, and if it is an inverse, and we'll talk about what that means, is that y equals f of negative x is how we write the inverse function, would have the points. What we would do is we just switch them. So instead of 1, -2, we have -2, 1. Instead of 2, 6, we have 6, 2. Okay? Instead of 3, 7, or instead of 7, 3, we have 3, 7. Instead of 10, 4, we got 4, 10. Right? Every x and y switches. So that's the most basic definition of what an inverse function is. Now, some of the things that we have to talk about depend upon if we have a function is its inverse actually going to be a function? Because a lot of times it's not, or we'll have to do some domain restriction to actually make it a function. So let's look at how we can do that. So a special type of function is a one-to-one function. It's a subset. Every function, right, is the big group. Some of those or a subset of those are one-to-one functions. It's like, I don't know, subset. In this case, each output has only one corresponding input, meaning that if you get a specific answer, there's only one way to get there. There's only one thing you could have plugged in to get you that answer. So I think an easy way to think of it is let's look at a function that's not one-to-one, something like y equals x squared. Okay, if we look at that, we know we have the point 2, 4 and the point -2, 4. Right? This is a function though, correct? Because it passes the vertical line test. Right? But if we look, the output of 4 can be arrived at two different ways, which means it's not a one-to-one function. So it's not a one-to-one function. The easiest way to see if a function is one-to-one is a one-to-one function passes the horizontal line test. Okay, now we know that to see if something is a function, it has to pass the vertical line test, right? Well, if it's one-to-one, it'll pass the horizontal line test. And what this says is a one-to-one function will be intersected by any horizontal line no more than once. Right? So if any horizontal line can hit it more than once, it's not one-to-one. Now it also has to be a function, right? So a vertical line test tells us if there's a function. Horizontal line test tells us if it is a one-to-one function, right? Meaning that each input has one output, but also one output only comes from one input. That's what it means one-to-one. So one element of the input matches up with one element of the output and vice versa. That's one-to-one, kind of how I think of it. A function f of x has an inverse if and only if f of x is 1-to-1, right? If it's not 1-to-1, like a parabola, right, it has a function, but its inverse is not a function, right, because it doesn't pass that horizontal line test. Now we'll do tricky stuff like we'll cut this in half, right? If you get rid of half of it, we kind of force it to have an inverse, but that's what we're looking at here. So to find the inverse of a function f, kind of a three-step process here. First, we verify that f is 1-to-1 and it passes the horizontal line test. Okay. For now, we'll probably want to sketch f just to see if it passes that test. If it does pass it, then we'll replace f of x or y if it's in there with x, so the output becomes the input, and replace x with y, input becomes the output. And again, we want to get rid of f of x, just make it y and then switch it out to be x. Then we isolate y and write your new function f inverse, or f inverse of x. Just a reminder, the input's still going to be called x. We just switch things around. And then just an important thing to note here is along with the x's and y's switching places, also the domain and the range of the two functions will switch. So if the original function f of x has a domain of the set A and a range of the set B, y equals f inverse of x has a domain of the set B and a range of the set A. So they flip. So for our first example here, we have, we're asked to sketch f of x and find f inverse of x. So we have this graph, f of x equals 3 over x plus 1. At this point, you could sketch it on your calculator. I think what we're looking at here, if I'm not mistaken, it's going to look something like that, right? So it's your typical hyperbola, correct? So is that going to pass the horizontal line test? Yeah, it does, right? It never hits it twice, right? Even though it gets really, really flat out here, it's still steep enough. So what fails is going to be like a parabola or like a big cubic or something. So that was our first step. Our next step here to find the inverse, I still like to rewrite this as y equals 3 over x plus 1. I like to just replace f of x with y right away. I find it's easier for me. Now at this point, I'm going to switch. So for me, I like to make a little note that I'm going to switch. So I'll actually sometimes just put a little wavy line and write the word switch to remind myself that this line and what comes next are not equivalent, right? Almost always with my work, the lines are equivalent as you go down the page. I think it's important to make a note if they're not, if you change it. So we'll get x equals 3y plus 1. So now in order to find the inverse, we have to isolate y. So here with this, what I would recommend we do is if the variable you're looking for is in the denominator, it's usually easiest to just multiply the whole thing by y, right? Multiply each term by y. There's other ways to do this, but I like this one. So we'll get xy equals 3 plus y. Does that make sense? I took this line, I multiplied the whole equation by y, so x became xy, 3 over y became 3, 1 became y. Multiplied through by y. Now at this point I have a couple y's, and if you try to solve for 1, you can't have y equal something in terms of y. It doesn't make sense. So what we do here, it's not obvious, but it's a trick that's really useful, is get all the y's on the same side of the equation. So I'm going to subtract y from each side. So we get xy minus y equals 3. Now these are not like terms. I can't subtract those, but I can factor out a y. Okay, so to do that, we'll get y times x minus 1 equals 3. Okay, now you have y times a quantity equals 3. Can we just divide by that quantity? Sure. We could say y equals 3 over x minus 1. And then we say f inverse of x equals 3 over x minus 1. A really nice, easy check that will usually show you if you made a mistake, it can go wrong, but it usually doesn't, is go ahead and for the original function, just pick a really easy number to plug in. Right? So if I look at this function, I would plug in 3. If I plug in 3 to that, I get 1 plus 1, so I get 2. Right? So this is a part of the original function. Now what do you think I'm going to do to the new function? I'm going to plug in 2. We plug in 2, we get 3 divided by 1, which is 3. Now is that a guarantee? No. We'll talk next week about how to guarantee that they're inverses. But it's going to catch most of your mistakes if you do it wrong. Okay, our second example here is f of x equals x minus 3 squared minus 2. This is a parabola. So right away, hopefully you're thinking, hey, that doesn't pass the horizontal line test, so it's not going to be an inverse. Now, what we can do, and what you'll see done, is if we graph this parabola, it has a vertex at, no, that's not even close. at 3, -2. Right, something like that. So what you'll see a lot of times is we're going to add a restriction to this function to make it 1-to-1. Because right now it's not 1-to-1, so we can't find an inverse. But let's go ahead and add the restriction that x is greater than or equal to 3. Right? Just like we do with piecewise functions, we can restrict the domain. So once we do that, not my best graph there, but we'll see that all this part will go away. I mean, not the axes, but. So now we have this graph. If I put the restriction on it, is it now 1-to-1? Sure, now it is 1-to-1. So then I can go ahead and find the inverse. So if I rewrite it as y, and okay, here also, let's go ahead and do this while we're at it. For this original function, we just said the domain is x is greater than or equal to 3. Like we picked that, we've made that a rule. So what would the range be in this case? Well, our lowest y value is -2, correct? So the range would be y is greater than or equal to -2. When we find the inverse, the domain will be x is greater than or equal to -2, and the range will be y is greater than or equal to 3. They're going to flip-flop. So let's just see if that happens. So here we get y equals x minus 3 squared minus 2. So we're going to do the switch here, right? We're going to switch up x and y. So we get x equals y minus 3 squared minus 2. And we just need to isolate. Now what you want to do here to make it much easier is we really don't want to square this thing, because if you square it, you'll get a y squared and a y. Then maybe you could factor, you might have to use the quadratic formula. I'm not that energetic this morning, right? I don't want to do all that work. So what we could do here is let's add 2 to both sides. And then we have y minus 3 squared. Now I'm going to square root both sides. And this is where, if we didn't have a domain restriction, as soon as we square rooted and said, hey, I need a plus or minus sign, we'd be thinking, that's not going to be it's not 1-to-1. But we'll just write it here for now and we'll investigate what we want to do. So we square root both sides, and we get y minus 3 equals plus or minus the square root of x plus 2. And then we get, add 3 plus or minus x plus 2 equals y. So that's starting to look like that f inverse of x equals 3 plus or minus radical x plus 2. But we have to decide, do we want the plus or do we want the minus? We can't have both, right? It's not a function if we have both. So if we look, we know that because of this property up here, because of this domain and range, we know that for our new function, it's going to have a domain of x is greater than or equal to -2, and a range of y is greater than or equal to 3. Right? So the smallest output can be 3, correct? So if I take 3 and subtract something, it just got smaller, didn't it? Which would be out of our domain. So what we do is it shows us that we do want the plus sign there. Another way with these parabolas when this happens is if you kept the right side of the original, you usually keep the positive side of the inverse. If you keep the left side, you end up keeping the negative side. But you just want to make sure you're in agreement. So, as we work through with functions, we just want to keep in mind this whole idea of domain, range, how they're flip-flopping, how they can work with that. So we saw a couple here, this plus or minus. The last one we saw that whole factor out the y and divide thing. So we're looking at some pretty cool algebra tricks here that might be helpful.